Today we're going to be graphing exponential and logarithmic functions. So we're going to be performing transformations to the parent exponential and the parent logarithmic function. So the first thing I want to do is review that parent exponential function, and it looks like this. I'm going to zoom in here so you can see y equals 2 to the power of x. You might also see y equals e to the power of x, right? It's just a base of e. So what's our domain for this function? The domain is all real numbers. In interval notation, we write it negative infinity to infinity, always using those parentheses when we write infinity. Our range, because that asymptote right here is at y equals 0, that means it will forever, your function will forever and ever approach that asymptote. It will never, ever touch it. So our range is from 0, not including 0 because there's an asymptote there, to infinity. The y-intercept right here, that's a key point, is at 0, 1, and your horizontal asymptote is y equals 0. So when we look at transformations to this parent exponential function, you might see it written looking like this, where all these different letters mean something. That number right out in front, that's the value of a. That's your vertical dilation, which stretches or compresses your y, all of your y values, right? It affects your y values. It's a vertical dilation, so that will change your y-intercept. If it's up here and it's in your exponent, right next to the x, or if your x has parentheses, it's right outside of that, but it's in your exponent, that's going to be your horizontal dilation. That can get pretty tricky, but I'll show you, and it's confusing for students a lot of times, but I'll walk you through that. And then obviously, if it is in your exponent, it's a horizontal translation, like x minus 4, okay? You'll be moving right 4. If it's x plus 4, you'll be moving left 4. So what I like to tell students is this horizontal translation, it kind of does the opposite of what you think it would. And then plus k at the end or in the beginning, we'll see it different ways. But it's not in your exponent, it's not multiplied by b. That is your vertical translation. It's your shift. Your y-intercept is this value right here, a, right? So it's 0a. So let's look at some examples. The directions say graph the exponential function given, then state the transformations from the parent function, its domain, range, and horizontal asymptote. So let's look at example number 1. In example number 1, 2 to the power of x minus 5 plus 1. So I see that this x minus 5, that is in my exponent up here, x minus 5, and then this plus 1 is all by itself. So what's that going to do? That x minus 5, that's your horizontal translation. It does the opposite of what you think it would. It doesn't move left 5, it moves right 5. And then plus 1, that's going to move our function up 1. Okay, so the entire function gets shifted to the right 5 and up 1. So we know that our exponential function has a horizontal asymptote at y equals 0. So this right here, this up 1, that's what's going to affect that asymptote. So let's move that entire asymptote up 1. So now the new asymptote for this function is y equals 1. We know that the key point in our parent function is right at like 0, 1, right? It's right above that asymptote on our y-axis. But if we shift this entire function to the right 5 units, 1, 2, 3, 4, 5, now that key point is right here. What is that key point? It's not 0, 1, it's going to be 5, 2, right? So now we can just graph this function like this, right? It looks the same. We didn't dilate it, we didn't flip it, we didn't do anything like that. So the domain stays the same, negative infinity to infinity. We did, because we shifted this function up 1 unit, our range is not 0 to infinity anymore, it's 1 to infinity. And remember, we're not including that 1 because that's the asymptote at y equals 1. Let's move to our example number 2. Example number 2, negative 4e to the power of 2 times x. Might have to zoom in a little bit more. Okay, So this -4 right here, that's going to be your y-intercept, right? That's your a value. Let's say y-intercept is at -4. So I'm going to go ahead and graph that. That's at -4. Have we moved up or down any? We haven't. So the asymptote is still going to be at y equals 0 because we're not shifting this at all up or down. So what's going to happen? So our y-intercept is at -4. How would we describe that when we're writing our transformation? So the negative out in front is going to reflect across the x-axis. So that entire function flips upside down vertically, right? It flips across the x-axis. And we would call that 4 a vertical stretch by a factor of 4. And then that 2x on the inside, remember when it's in the exponent, it affects horizontal, right? It's your horizontal dilation, it's your horizontal translation. How would I describe this? You might recall when we did transformations of functions in Unit 1 that I would describe this as a horizontal compression by a factor of 1/2. I've also seen this be called a horizontal stretch by a factor of 2. And I mean, to be honest, if you just said horizontal dilation by a factor of 2 or horizontal dilation by a factor of 1/2, I would be okay with that. I would go with what your teacher says, but I've seen it both ways. I like to write it like this. It's a horizontal compression by a factor of 1/2. Okay, so because I haven't moved left or right, up or down any, we're not going to, or really left or right, you're not really going to see that horizontal compression by a factor of 1/2 like how I want to show you in later examples. But generally speaking, if you just take that exponential parent function and flip it, and you know it's going to across your x-axis, it's going to look like this, okay? And if you get the kind of general shape, that's why there's not like an actual grid on here. We're just drawing a rough sketch. That's what it is going to look like. So we're just reflecting it across the x-axis, and that does not affect the domain. It's still -∞ to infinity, but because it was flipped across the x-axis, that does affect our range. It goes now from -∞ up to 0, not including that asymptote at y equals 0. And now let's move on to examples 3 and 4. I need to move more quickly through this. Okay, f of x equals -1/2 times 2 to the power of x. So this y-intercept is going to be that a value, right? So y-intercept, that's just a good starting point, is at -1/2. Okay, if that's -1, there's my y-intercept. Are we moving up or down any? We are not. So the asymptote is still going to be at y equals 0. And how would I describe this? I know the only thing that's happening to our parent function, right, y equals 2 to the power of x, is we've added this -1/2 in front. Okay, what does the negative do? It's a reflection across the x-axis, so it's going to reflects across the x-axis. And then what does that 1/2 do? That is a vertical compression by a factor of 1/2, right? So all of our y values, whatever they were, they become half of what they were. Okay, so if we reflected it, if it was just -2 to the power of x, that y-intercept would be -1, right? But because it's -1/2, now it's half. Our y value is half of that, right? What's half of -1? It's -1/2. So it's going to look like this. It's going to take this general shape, right? So we've reflected it across the x-axis. It looks like that. Our domain is not affected. -∞ to infinity. Range is -∞ up to our asymptote, which is y equals 0. Let's move on to example number 4. This is the last exponential function before we move on to logarithmic functions. So f of x equals 6 times e to the power of negative 2x. Okay, there's a lot more going on here. Let's just focus on our good starting point, which is our y-intercept, which is at 6. So I'm going to go ahead and I'm going to graph that y-intercept at 6. Okay, so we can write that down. This is a vertical stretch by a factor of 6. Okay, and that's why that y-intercept is no longer at 0, 1, it's at 0, 6, right? Okay, so what's happening horizontally? We've got a negative and a 2 in front of that x now. So what do each of those do? So that 2, how I will describe this, is it is a horizontal compression by a factor of 1/2. So horizontal compression by a factor of 1/2. So it's 1 over b. That's how it affects it. I know that's really confusing. If you just say horizontal dilation by a factor of 2, horizontal dilation by a factor of 1/2, I'm sure that's fine. And because that negative is in our exponent, that's a reflection, right? When a negative is in front, but what is it reflecting across? It's not reflecting across our x-axis anymore, right? We don't have opposite y values. It's reflecting across our y-axis. We've got the opposite of all of our x values, so it's reflected across the y-axis. So this is really confusing for students to think about. You got to think about, like, what does that original function look like, right? It's like your exponential growth function. So instead of a growth function, if I flip it across that y-axis, it's going to look more like a decay function. So it looks like this. And we still have that asymptote at y equals 0 because we didn't shift this up or down any. So the asymptote is still there. Domain is still all real numbers, negative infinity to infinity. Range is from 0 to infinity. Let's move on to logarithmic functions. So your parent logarithmic function, and I'm going to change colors here just because. Let's do this color. Okay, here's your parent logarithmic function. This is just y equals log base 2 of x, okay? So your domain, we can see, I haven't really talked about inverse functions yet, but instead of the asymptote being y equals 0, it is now x equals 0. It's vertical. Instead of a y-intercept being 0, 1, the x-intercept is at 1, 0. Instead of the domain being all real numbers, the range is all real numbers. And this is how I write it in interval notation. And instead of the range being from 0 to infinity, our domain is what is 0 to infinity. That's our parent logarithmic function. This is our starting point for the next 4 examples. So all of the transformations are the same as exponentials. Okay, all of these are the same as exponentials. But this right here, your horizontal dilation, our vertical dilation isn't changing our y-intercept. The horizontal dilation changes the x-intercept. Okay, so let's move on, and the x-intercept is a 0. Okay, so let's move on. And in example number 5, negative 3 times the log of x plus 4. We're going to do the same things for these next 4 examples. So that negative 3 out in front, I'm just going to look at this right here, that negative 3. So what's happening here? It's going to reflect across the x-axis, right? So it's going to flip. It's a vertical dilation or stretch, whatever you want to write, by a factor of what? 3. Factor of 3. And it's a shift up 4 units, right? Okay, so we're not moving left or right. That's what's going to affect the asymptote in this for the logarithmic function, right? Up or down affected the asymptote for exponentials. Left or right affects the asymptote for logarithmic functions. So that's kind of where I like to start, right? the asymptote stays the same. It's at x equals 0. Now, because we're moving up 4, and it's a vertical dilation, okay, by a factor of 3, that key point, okay, is not at 1, 0 anymore. We're moving up 4, so that key point is actually going to be at 1, 4. Okay, that's your key point. Or, yes, 1, 4. And so if you think about what your parent function looks like, it kind of looks like that, right? So if I reflect it across that x-axis, it's now going to look like this, right? Something like that. It's going to just be that general shape. Just draw a little rough sketch there, and that's what it's going to look like. So our domain, has our domain changed? It has not. It's still from 0 to infinity. Range is still negative infinity to infinity. And now we can move on to example number 6. So negative log 2 of x, or I'm sorry, not 2 of x, negative log of 2x. So what happens here? That negative out in front, that's going to reflect across the x-axis. So let's write that down. That's going to reflect across the x-axis. And that 2 in front of the x, right? It's inside the x, so that's a horizontal. It's going to affect our function horizontally. We would call that a horizontal compression by a factor of 1 over 2, right? So a horizontal compression by a factor of 1/2. Again, like I said, I have seen horizontal stretch by a factor of 2. Just make sure that horizontal is in front, right? So, I mean, I have seen that horizontal dilation by a factor of 2, horizontal dilation by a factor of 1/2. The horizontal stretches and compressions really can confuse students a lot. Okay, so now that we've got that going, are we moving left or right? We are not, so the asymptote is still going to be at x equals 0. And I'm going to write that down here. X equals 0, and I know that that key point is always at 1, 0, right? It's just 1 unit to the right of our origin, right? It's at 1, 0. Well, in this case, because we are compressing this by a factor of 1/2, all of our x values are going to be half of what they were. So instead of 1, 0 being our x-intercept, it's now going to be at 1/2, 0. So I'm going to write that here, 1/2, 0, half of what it was. And because that negative is out in front, I drew that parent function shape right up here, right? It kind of looks like that. Because we're reflecting it across our x-axis, it's going to take on this shape. Oh, and I drew it on the other side of that asymptote. It shouldn't look like that. It's not supposed to cross that asymptote. So it's going to look like that. It's going to be that general shape. So your domain is still from 0 to infinity. Range is negative infinity to infinity. And the asymptote is at x equals 0. So let's move on to 7 and 8. So we've got the natural log function here. And it's still going to take that same shape, so it's going to look exactly the same. Let me show you. So number 7, this is the natural log of x minus 4 plus 3. So this x minus 4, inside those parentheses, that's your horizontal shift, right? Your horizontal shift is what moves that vertical asymptote. So I'm going to write that here. It moves the vertical asymptote. So instead of that vertical asymptote being x equals 0, if I move this right 4, it's now x equals 4. So I'm going to write all of that down, right? This is a shift right 4, and that is what affected the asymptote. The asymptote is now at x equals 4. Okay, what else is going on here? We've got a plus 3. That's going to move the function up. I wrote a 4. Up 3 units, right? So I know that key point is always 1 to the right of the asymptote. Well, if I move it up 3, it's now going to be right here. What point is that? that point is now at 5, 3. If it was at 1, 0, and I moved it right 4, right 4 units from 1, that's 5, and then up 3, that's 5, 3. And then I'm not reflecting it across any axis or anything, so it's just going to take the same shape as our parent function, just like going up and out like that, right? So our domain, and that's not a very pretty graph, but that's what it's going to look like on here. The domain, because I moved it right 4, is now from 4 to infinity. Did not affect the range. It's still negative infinity to infinity. And let's move on to our last one. And here we go. Number 8, f of x equals 3 plus 4 times the natural log. Let me close that. Natural log of x minus 1. So this looks a little different. A lot of times you might see the plus 3 on the end, but we see it out in front. And that 3 right there is actually our shift up 3. What else is going on here? That 4 out in front, that's going to be a vertical stretch by a factor of 4. And then that x minus 1 inside the parentheses is going to move this right 1, which that horizontal shift to the right 1, that's what's going to move our entire asymptote. Instead of at x equals 0, that asymptote is now at x equals 1. And that key point, that would be normally to the right of our asymptote, because it has been vertically stretched by a factor of 4, is now not at 1, 0, but, oh, I'm sorry, hold on, because it's been shifted up 3 units, that's rather what I should say, that's what's affecting it. Because it's been shifted up 3 units, it's now not 1 to the right, it's 1 to the right and up 1, 2, 3, right here, okay? So what is that? Instead of it being 1, 0, it's moved right 1, okay, that would be at 2, 0, up 3. That means this point, this key point here, is at 2, 3, okay? Right 1, up 3. So the vertical stretch by a factor of 4, that's what's going to make it look like if my parent function looks like this, right? Kind of curves like more quickly, you could say, like that. If it stretches it, it's going to kind of look like this. Like that stretch is not going to curve so quickly, right? It's going to have more of a, oh my gosh, that's terrible looking, but that's what it looks like. Okay, so our domain is now from 1 to infinity. Range has not been affected, negative infinity to infinity, and the asymptote is at x equals 1. And that concludes your notes over graphing exponential and logarithmic functions. I hope it was helpful.